Okay, so I want to give an example of the random features regression. Here's an example. And random feature regression example. And that example is the train only the last layer of neural network. So that let's put this with hyphens. Train only the last layer neural network. So to do the training only the last layer neural network, you're going to have this big, gigantic, deep neural network. And maybe it has D layers. And, that means there's a lot of parameters and things. So there's D minus 1 layers at the beginning, and there's this last layer, which is the Dth layer. And normally in a neural network, you train all of these parameters. So all of the parameters are being updated. But in the train only the last layer neural network, you do something very silly, which is you freeze the weights of the first D minus 1 layers. So these say frozen. So all the weights and biases in the first D minus 1 layers, whatever they are initialized to, they're frozen at initialization. So whatever they are initialized to, they don't change. And the last layer, the Dth layer, that is the only layer that you train. Okay, and by doing this, so first of all, the model becomes a linear model. So we're not going to apply the nonlinearity on the last section. So it's exactly a nonlinear, or although nonlinearity is gone with respect to the weights. So what is the model? It's going to be something like this. Let's call it FD for the depth D. How does it depend on this? It's going to be whatever is the output from the first D minus 1 layers, and then we're going to just do the weight matrix W plus the bias B. So the parameters are only from this last weight. So maybe let's call this WD, the last layer, and the biases from the last layer. So and if you write this down carefully, you'll see that this is precisely a feature regression where the features are the output of the first D minus 1 layers. So this is exactly a feature regression model, and the features are whatever the output of the first D minus 1 layers are. So the features 5x are equal to f of D minus 1 of x theta. Okay, and we said that the weights and biases for the first D minus 1 layers are frozen at initialization. Well, you initialize randomly. So not only is it this, it's actually this at time 0, which is initialized randomly. So this is precisely a random feature regression model. So the random features are whatever comes out of the first D minus 1 layers of the model, and we're only training the last layer. That's exactly doing this regression because we have linearity. So it's very nice. And what did we say? We said that in the limit that the number of parameters goes to infinity. So that's the width of the last layer. In that limit, the kernel K, which is the thing that determines all of training, that this converges to. So normally this is a big sum, but in the limit that the width of last layer goes to infinity, the kernel K is converging to this expected value. The expected value, and it's the expected value of the features that you get. So what is it in this case? It's the expected value over all possible initializations, theta 0, of f of D minus 1, x theta 0, fd minus 1, x theta 0, x prime. So whatever two inputs you put here, you get this. So this is just an application of the random features regression model where it happens that the features are a neural network. And as the width of the neural network goes to infinity, that's the same as the number of features going to infinity. That's the limit where the kernel approaches the expected value. And this thing is something you can actually compute. And in the later videos on neural networks, we're going to compute this. So this is something people call the NNGP kernel, or the conjugate kernel, sometimes So this thing has a name, and you can compute it, and you can figure out what it is. And in fact, there's some computer programs out there that figure these things out. Given the architecture of the network, they'll compute this for you, and you can do everything from that. So what is the point of all this stuff? The feature regression model comes up in neural networks in this silly model where you only train the last layer. And there it's obvious why it comes up. It's also true that it's going to come up in the neural network where we train everything, but that's a little more subtle, so that'll have to wait till we get to that.